Uh, Good evening, everyone. I'm not Michael Jordan. I know you've come to hear Michael Jordan, but I'll inflict a small little presentation on ICTS to you and also welcome you to this institution. Usually we do this on the first day of the meeting, all the participants for the program that's been organized, but I couldn't do that yesterday, and this is anyway a good occasion to do that. So I'll sort of tell you a little bit about this institution that you're at. But before that, let me thank all the organizers who put together this wonderful meeting, Praneeth and Sandeep, and the absentee ones, Vivek and Devavrat, and also all the speakers who've come here, battling many issues, I'm sure, of visas and other things. But those of you who made it here in person, thank you very much. I'd especially like to thank Professor Jordan for agreeing to give these Turing lectures, a series of 3 lectures. ICTS has, as I'll say, flagship lectures in the physical sciences, mathematical sciences, and in the computing and computer science, engineering, and biology, which Turing contributed to. So we have the Turing lecture series encompassing these areas. It's been given by a number of very eminent scientists in the past, mirroring the Chandrasekhar lectures in the physical sciences and the Ramanujan lectures in the mathematical sciences. But you'll hear about Michael and so on from Praneeth. To ICTS, this is the aerial view of the campus. You may not all be able to have this view unless you climb up to the water tower, which you see on one corner of the campus. And this is actually a bit of a dated photo right now. If you climb up, it's much more green. And you'll see, I mean, it's just in a few years that I think we've had all this green grow, but it's not the geographical, the layout of the institute that I want to tell you about, but a little bit about the institute as it is academically. It's one of the newest centers of TIFR and one of 3 in Bangalore. And it's unique in its mandate in combining research, which is an intrinsic part of TIFR, so fundamental research in various areas, which I'll take you through, but importantly, programs, and programs of the kind that institutions, with similar institutions in physics, mathematics, computer science, etc. have. So I've just listed a few of them here, but so in that sense, we serve as an enabling center and a hub for the Indian scientific community. And I'd like to stress that it's not a conference center. We are an academic institute in the end, and research is at the core of our identity. But we, our researchers, together with the help of the academic community at large, we try to curate special programs which can bring together researchers from within India and the rest of the globe to come and spend time, discuss, come up with new ideas, and hopefully push the frontiers of knowledge. And so these programs are in theoretical sciences, broadly construed, so physics, mathematics, computer science, quantitative biology, recently climate sciences, and it's an expanding canvas. And these programs are combined in a way with our research. Often our researchers are involved in the organization of programs, but not necessarily, as this program shows. We also combine them with outreach. So we have a parallel program actually going on in mathematics right now. And some of you may be from that program. And one of the participants from there gave one of our Copy with Curiosity outreach lectures this weekend. So they're kind of intertwined, all these 3 mandates, 3 components of our mandate. This is a watercolor of our library building. It's a signature building of ICTS. If you haven't seen it, please go in. I mean, please, you can see it from outside, but please go in, and if you wish, spend some time there. You can, it's a very nice place to hide away, to and to be a bit inspired. And that's what this mathematician, he sketched this watercolor and gifted it to us. So any of you who have similar artistic sort of inclinations or come up with something, please do share it with us. We'll be happy to sort of showcase it. This is a collage of our researchers in many areas. The areas currently, so we have about 30 faculty in various forms, about actually now closer to 90 PhD students and over 30 postdocs. The areas include in the physical sciences broadly described. So in the mathematical sciences, dynamical systems, PDEs, climate sciences, geometry and mathematical physics, probability theory, which in some ways intersects with the program here. And recently theoretical computer science, where we have Gopakumar, who we have stolen from TIFR Kolaba, join us. And in the mathematical sciences, it's astrophysics, including gravitational waves and black holes of both the stellar and the galactic kind. The complex systems is a very broad term which encompasses statistical mechanics, condensed matter physics, quantitative biology, fluid dynamics, and so on. And finally, string theory, quantum field theory, and so on, for a small bastion of that area of science here. So the collage of some of our programs. But programs are organized, as I said, by the global scientific community. There's a twice-a-year call, and I want to advertise this. It's in the end of the year and the middle of the year, so very easy to remember deadlines. So you can submit it at any time, but these are deadlines for consideration by the program committee. Right now, June 30th is over, but we've extended it to July middle. We often give a little bit of a leeway of a couple of weeks. And then the proposals, programs here are typically 2 to 3 weeks long. We like to have a pedagogical component, and even some of the shorter programs like this one do have that, because one of the ideas of ICTS is to train young researchers, and so that's an important component. We have discussion meetings like these, which are less than 2 weeks, which are don't necessarily go through the program cycle, which the program cycle is currently, the current call is for programs from October 2024 to March 2025. So it's about a year and a half in advance. So you have to plan ahead for a long program. But discussion meetings we are a little more flexible. We try to find interstitial vacancies in the calendar and then try to adjust, have some discussion meetings depending on the areas and the excitement. So there are actually closer now to 35 programs in a year. Things are going on in parallel, and over 2,000, closer to 2,500 now external participants. So there's always a flux of people through the campus, which keeps it alive. There's a large international involvement. And I think it has grown to be a science hub. People see it. We serve as a facility for the country and the community and the global community at large. And we try to keep track of publications coming out of this. So over 600 publications have come out of programs that have been acknowledged by people in their papers. So if you do have a paper that comes out of discussions here, or which in any way was enabled by discussion, by your participation here, please do acknowledge it and send it to our program cell. As you can imagine, it helps us in making the case for funding. So that's something I'd like to stress. We've had over 600 in the past 5 years. There's a permanent repository of all the talks, like this one, all the ones in the meeting. And there's a YouTube channel, ICTS Talks, which where you can find the whole collection. And it's I think, a very valuable resource and has been used as such by people. So these are the special lectures. I mentioned them, and there are others, more specialized ones. Finally, just a few words about the outreach, the third component of our mandate. it's something we take seriously. We have science outreach along sort of 3 axes: science communication, which is sort of things everyone does, public lectures, talks, and the Copy with Curiosity that I mentioned. It's held at the planetarium once a month. You can actually all our events are live streamed. So even if you're not in Bangalore, you can sort of tune in through our YouTube channel and watch these programs, watch these events. But then the second, along the second axis is more interactive science exhibitions and sort of engaging with the public. We have an online one during the pandemic on Cosmic Zoom. There was one on the weather recently, on climate change. And finally, science pedagogy, involving working with some of the schools in the nearby, in the neighborhood, and rural Karnataka, as you see we are in. And a math circles network inspired by the original ones in Berkeley and others. And here, I think we have Piyush, who is here, is one of the active people in this. It's a pan-TIFR network, which actually we involve, has had sessions run by people from institutions across the country, ICERs and so on. If any of you are interested in running these math circles, you can look at the math circles page on our homepage under outreach and get in touch with our outreach team or Piyush and me or anyone. And we really want this to become a widespread, sort of just like the original one at Berkeley, seeded by MSRI, has spread to now a couple of hundred math circles across the US. We would like this to sort of grow in India and be a sort of a movement, if you wish. So these are some of the things ICTS does. I hope you'll all have an enjoyable stay, and I'm sorry to have taken up, come between you and the talk today, but I'm sure it'll be worth the wait. Thanks for your attention. Over to Praneeth.
Yeah, so we are very delighted to have Professor Michael Jordan from UC Berkeley giving the Turing lecture today. And Michael Jordan is a very famous computer scientist, machine learning. So he has done fundamental contributions in various domains such as machine learning, cognitive science, statistics, optimization, and is currently also looking at connections between machine learning and economics. He's a member of the National Academy of Sciences, National Academy of Engineering, American Academy of Arts and Sciences, and has won several awards. And he has particularly instructed me to keep these introductions short, so I cannot list all of them. And in particular, IEEE John von Neumann Medal and David E. Rumelhart Prize. And finally, one of the things that's really inspiring is that Mike has, over the course of the last 40 years of his research journey, has mentored over about 150 postdocs and PhD students, many of whom are currently leaders of the field in various disciplines, including machine learning, statistics, and so on. Without further ado, over to you, Mike.
Which is we have here today Professor Shobho Bhattacharya, former director of TIFR, and I'd like to invite him to give a memento to Professor Jordan on behalf of ICTS. So it's a small sandalwood statue of the Buddha. So it's. Thank you. Thank you.
All right, with all of that wonderful preview, I'm ready to go. I hope you are. So it's an honor and a pleasure to be giving these lectures. I rarely get to give 3 of them, so that allows me to go more slowly than usual. I usually tend to talk too quickly, so I will be a little slower. So I'm principally a mathematically inclined researcher, so I would love to just write down some theorems for you and show you how great they are and all. But I'm also more and more an engineer, realizing that our kind of mathematics is having a big impact on the real world. And so if what you're doing is having an impact on the real world, by almost definition, you're an engineer. And so I think it's responsible to start thinking about what's the engineering field that's happening here and what should be this engineering field. So let me just understand the audience a little bit before I get going. How many of you would you call yourself mathematicians? Just because I have no idea what the audience is. So like about a third of you. How many physicists? How many computer science? Okay, another third. How many statistics? Okay, well, thank you for coming. I'm glad to have a few. That's my home field. Economists, are there any econ people? Yeah, maybe. Okay, that gives me a little better. How many of you are faculty? Okay, about half. How many are students? The other half. How many are neither? Okay, we're all students, aren't we? Okay, so like I said, I'm a person who wants to write down some theorems, but nowadays you can't pick up a newspaper without seeing the buzzword AI. And so I need to talk about what that means and what it doesn't mean, and kind of frame a little bit about where research should be going in this field. Because the framing right now is kind of completely unconnected to the actual research. So let's talk about that. Okay, so I hope I was supposed to get this. I think I've got to click something before it. Let me see if it now works. There we go. Okay. All right. So what's now being called artificial intelligence, for years it was called machine learning, and I'll talk a little more about what machine learning is. But machine learning is, in some sense, the engineering branch of statistics, if you will. That's kind of a good way to think about it. Okay. Statistics really was the field aimed at helping scientists out. If there's, you do a hypothesis test, is there a new particle or not, or, and so on. And statisticians didn't really care so much about the engineering discipline. They were interested in science and math. Okay, so there was a gap, and people came in, computer scientists mostly, and filled that gap and started doing statistical work without really knowing that's what they were doing. And that was the origins of machine learning. Now, there really are kind of two parts to any decision-making under uncertainty field, like machine learning. One of them is finding the patterns, and the other is making the decisions. And the finding the patterns part has become dominant. Okay, so that's what deep learning is, and that's what recommender systems are, and so on. And it's become a commodity. You can now download software, and any of you within 10 minutes can be up and running a state-of-the-art prediction system. Companies can be built on that, and they are. And so it's having a big impact in the world. Now, when things start to have an impact in the world, unpredictable things start to happen. Okay? Dynamical phenomena arise that you wouldn't have expected. And a lot of that has to do with decision-making side of this field. You don't just make predictions in life, you make predictions and you act on them. And so I'm going to focus more on this. This is the other part of the field. There's many people active there, but just much less prominent than the pattern recognition side right now. So I hope to bring it to prominence here. All right, now the other part of this is to remind ourselves that we're not just academics. We're trying to build systems that somehow work in the real world and somehow make human life better. And so actually the history of machine learning is best told not as an academic discipline that discovered some ideas that had a big impact. That's just not true. Really, it emerged as a powerful force in industry. Okay, so already circa 2000, there were very large scale systems built in companies like Amazon or Alibaba and all to do supply chain management. Because supply chains have to do with a stochastic process that's very, very complex. Ships moving across the ocean and possibility of a strike in some city and all kinds of things happening. And you have to predict all that so that you can serve products on a timely basis. Products are usually put together from multiple pieces. You have to model all of that. And nowadays, I think Amazon serves 1 billion products to hundreds of millions of people. And the supply chain to support that, it just boggles the mind. So this is the world's largest stochastic control system ever conceived of. Okay. So you must imagine behind that, there must have been some algorithms. It can't be done by human beings writing this on paper, and it definitely wasn't. In fact, I spent some time in Amazon. I kind of learned a little bit how they built it. It was actually built mostly by chemical engineers. Interestingly, not computer scientists, because they were used to thinking about systems and flows and sort of thing. Anyway, they built it, and the algorithms they were using were something called random forests. So it's like 20 years ago, so they weren't using neural nets, but random forests are just basically roughly as good. But you had to do it at scale. So they needed tens of thousands of computers to support the random forest algorithms, and they had the data and all. So they built what became the cloud. So this is actually the history of the cloud. Where did the cloud come from? That was because Amazon used random forests to do supply chain management. That's the actual history. All right, so already there was algorithms that are basically gradient descent algorithms. There was massive amounts of data, and there was computing of the cloud kind. So it's not that different from what we have now. Right, but and moreover, it had a huge impact on our society, on billions of dollars of productivity gains. The second generation for me was about 10 years later when a lot of these companies started to realize they have a lot of data, not just about ships in the ocean and strikes and all that, but they have data about human transactions, what people bought and what they do and so on. So they started to build recommendation systems. That recommendation systems are just pattern recognition systems. They find patterns. They say if somebody buys these books, a lot of physics books and a lot of books about India, and someone else comes in, it looks like they're Indian physicists, I'll recommend those books to them. All right. And so it's a low rank matrix factorization and so on. If you do that at scale, you need, again, tens of thousands of computers, and you need gradient descent algorithms, and they did that too. And now it had a very big impact worldwide. Recommendation systems are used everywhere now, and you don't even know they're being used, but they're used everywhere. And they're really, I'm going to get to this a little later, but more like a social phenomenon. They're not just an algorithm. The third generation to me was what we're in right now, where all the hype has come and all the talk about AI and all the nonsense. Now, what changed? Well, none of the algorithms really changed. They're a little bit different. There's a transformer that does it. It's a little bit of a change, but not really. It's gradient descent based on large amounts of data and predictive. It's making predictions. That's all it does. What changed is that the data was now human output. It was speech and language. And so it's now doing a good job of predicting that instead of predicting supply chain problems. And so we kind of knew it was going to be good at that. It's probably better than most of us would have guessed. It really is very impressive. But because it looks like a human doing it, people started to use the AI buzzword. That came back. That had been dead, but it came back. And then the journalists got involved, and then the hype started, and all the CEOs start to be the ones who talk about the research agenda for the field, and they don't know what they're talking about. Okay. Anyway, in the meantime, I think something even more interesting is happening. Okay, which is the emergence of computers and data analysis at very large planetary scale to build new kinds of markets. What are markets? Those are things that bring together producers and consumers of various kinds. And that was done, of course, 3,000 years ago in all kinds of markets. That's why we're here. We wouldn't have done that if all this didn't, markets didn't arise. And there was mathematics eventually developed to help support this activity. But as soon as you start to go into the modern world at very, very large scale with all kinds of challenges and data analysis is possible, new kind of mathematics emerge and new kinds of challenges emerge. And that's what I really want to get at, because I actually think this is what's really already happening. Systems that responded to the pandemic within a year and a half, developed the vaccine, developed it, put it out. That was based on data analysis, a huge, massive data analysis, and cooperative data analysis, transportation systems, commerce systems, and all. It's all based on big data flows and networks. But we don't really know what we're doing. We don't have a science of this. We just have a kind of a few artifacts. So it's really interesting. Okay, so let's talk about AI. So there's this buzzword being used, and so really nowadays when you say AI, you just mean computers. Okay, so is there something actually happening? Well, again, if you look at the outside real world, yeah, something is happening, something is changing. And I think what's happening is it's the emergence of a new field of engineering. Okay, now most fields of engineering, they emerge about every 50 years or something, civil, mechanical, electrical, and so on. Most of them are based on there's existing science that tells you what to do, and then you have to scale it, and you have to make it robust and make it really work with real humans and all that. So I know a little about the history of chemical engineering. I dug into it a little bit. I mean, the term was already being used in the late 1800s, but it emerged in the 40s and 50s with polymers and complex chemical design. And before that, of course, there was already quantum chemistry. There was already fluid mechanics. So you knew what happened when molecules came together. You knew how to make new molecules in the lab. But the idea that you could do that in a field and make a factory that would take in vast quantities of things and actually produce output, that was hard. It was an interesting challenge. And some of the first factories that were built didn't even work at all. Some of them exploded and killed lots of people, and it took 20 years. And in that 20 years, new mathematics were developed, new thermodynamics at scale, new kinds of fluid flow ideas, all kinds of things that is now called chemical engineering. And it's not just engineering, it's got its own mathematics, right? Same thing in electrical engineering. Before electrical engineering became a thing, there was already Maxwell's equations. So in some sense, the phenomenon was completely understood, right? But then the idea of how would you bring electricity into a city and then into a home and not burn down all the homes? How would you build circuits? How would you do communication over these waves? All that had to be done, and that was called electrical engineering. And of course, it had its own mathematics. Some of it just started with Fourier theory and so on, but then it quickly got much more interesting and complex. So it wasn't just engineering. All right, so I hope you can see where I'm going. That this field is now a new engineering field that's based on what? Well, in understanding of inferential ideas, statistical testing, algorithmic ideas and complexity and scaling and building systems, but not a lot more. It's not as deep as quantum mechanics and Maxwell. It's just not, all right? But we're nonetheless building these big systems like factories and hoping they work, like a big social network or a big payment system or something. And sometimes they work and sometimes they really don't, because we have a little understanding. So we have to develop the understanding and develop the new mathematics and develop the tools and do all this. Society needs to do this. And the problem is that this is being warped because of these old AI aspirations, which are now coming back to the fore. So let me dig into that for a moment. Okay, so in 1950s, the term artificial intelligence was invented. John McCarthy, and I don't want to say that was a bad idea. It was a good idea. So it was almost a philosophical aspiration. Computers had been invented, and they had hardware and software. It looked like the mind in the brain, and it looked like we could start to understand what's happening in our own brains, and we could develop intelligence in a computer. That was an interesting, almost philosophical task. What would that do? Who knows? But let's try to do it. So that's what these people did, and AI emerged in that era. It didn't succeed. It basically didn't succeed. The ideas that were developed, it's just a hard problem. We don't understand intelligence. Moreover, intelligence is not really one thing. You know, ant colonies are intelligent. You know, economic systems are intelligent. They respond in adaptive ways and so on. You know, what kind of intelligence are we talking about? Just the kind that comes out of a bunch of neurons? So it never was very clear what the goal really was. But nonetheless, it was interesting. Again, what happened in the intervening 40 years was like search engines were developed, supply chain was developed, you know, and so on and so forth. All these things that aid humans, augment our intelligence. Okay, thought in a computer we still don't have to this day. I mean, these large language models are doing some mimicking of some aspects of thought, but they're not really thinking the way we do yet. Probably for quite some time, I think. Nonetheless, that became the goal. Let's understand intelligence. And moreover, now these artificial intelligent agents we create have to be autonomous. That was a strange step. Why do they have to be autonomous? Well, because if they're tethered to one of us, they're obviously getting their intelligence from us. They have to be all by themselves. Now that's kind of a show-off kind of statement. It's not good science or good engineering to say we're going to show off. So here's my robot. Look, it's doing all these things by itself. Right? And to this day, you're seeing all kinds of show-off exercises. You know, I saw a thing yesterday morning, like there was some orchestra in Korea being directed by a robot. You know, it's a show-off. The robot doesn't understand music, and it's silly. Right? But that became part of the agenda. It had to always be autonomous. There are cases where you want an autonomous system, one that goes into a burning house, maybe it could be autonomous, or one that goes to Mars, you know, something. But mostly you don't want things that are autonomous. You want them to be all connected and federated. You don't want a self-driving car that's autonomous. You want it to connect to all the other cars and communicate and be part of an overall system that has good flow and doesn't have accidents and knows what's happening around it and all, just like the air traffic control system. Federation is the key, and federation is a whole principle of itself. That's designed at the level of the system, not the level of the individual. All right, so I think that was a mistake. And it became part of the agenda without a lot of thought. All right, now, is there a alternative? Well, yeah, it's not that hard to think about. Let's don't think about taking a computer and making it replace a human and then see what happens. Let's instead think about the collective. What's the collective? Well, it's lots of humans, but also humans mixed in with computers, devices around us. All that is a big system. And that collective overall should be doing things that are good, that are helping, that are, you know, interesting, safe, effective, and all that. So if you're going to establish goals for the emerging engineering field, it shouldn't be like the Turing test. I hate to use the word Turing in this lecture, but you know, the Turing test was, can you take out a human and put in a computer, no one knows the difference? Okay, that's not a good goal for the engineering field. It doesn't lead you anywhere. Okay, so we got to talk about a different level of abstraction. Oops, forward too far. Okay, so again, mimicry of human skills is fine. You know, you could that's a sub area, but it's not the right one. The autonomy is dangerous. Moreover, there are new forms of collectives that can emerge if we put our minds to it. All right, and I'm going to talk a little bit more about that on the next slide. But we haven't thought much about intelligent collectives. Okay. We do look at like ants, you know, each individual ant is not very smart, but they can build ant hills and all that. And we do think about collectives of birds doing things like that. And if the physics people among us love to analyze those things as dynamical systems and so on and so forth, interesting emergent behavior arises. But that's more like the science of looking at something out there and understanding it. What about building things that have emergent behavior that's really interesting and helpful? You know, we don't think that much about that. Like, what about building better decision mechanisms at the level of the collective, like better ways to do budgeting? There's something called now participatory budgeting. It's a great example of this sort of thing. There's kind of new democratic mechanisms being explored where people come together in new ways. And there's a whole range of things to explore. And so this kind of thinking I'm actually getting from some of my colleagues. Here are 3 papers if you want to read more at this high level. You might want to have a look at. So the first one I wrote about 4 years ago, it's some of this, trying to push back about the AI hype. The second one brought in economics. And the third one is with my social science colleagues here, how AI fails us. And their perspective I found very, very helpful, which was that they think about the collective, they're social scientists, and they also didn't understand the whole point about autonomy. They said, isn't autonomy just a bad thing? Because if a system is going to be autonomous, it has to be developed also by a small number of people, right? Because if it's developed by 100,000 people, it's kind of not a lot of intelligence. So Wikipedia was developed by millions of people. It's not intelligent, right? The search engine's not intelligent, and so on. Even though they've changed our lives as much as anything else you can think of, they're not intelligent. So they said, well, that's kind of weird. And moreover, if it has to be developed by a small group of people, that's just a bad dynamic. That leads to some companies owning everything. And that's exactly what's happened. You see OpenAI that says, we're going to make it all open. It's not open. They possess it. All right, so it's just the wrong dynamics. And my social science colleagues have dug into it in this paper, where I helped a little bit with sort of the economics angle. All right, so now if you go to the machine learning people, which I'm one, and you say, well, haven't you thought about the collective? Don't you care? They say, sure, we've got federated learning. So what is federated learning? It's this kind of diagram. And it was really, so there's a central server, and it wants to take in lots and lots of data to build even a better model of something, speech or language or whatever. And where does it get all its data from? Well, it would like to grab some data from some edge devices like cell phones. Okay. So the machine learning agenda became, how do you grab the data? How do you steal the data? How do you pretend that you're treating it with privacy mechanisms? Okay, reassure people that you're not, and then how do you compress the data, and how do you do, the machine learning on the compressed data, and so on and so forth. There was a whole agenda, and there's now hundreds and thousands of papers about this, right? Right, but there's something missing from this diagram entirely, which is that really, this should be thought of as an economic system, okay? Because the people at the edge are not just edge devices, cell phones, those are people. And people are creating things on their cell phone. It's not just what they said, it's not just speech. It's that people are now writing songs on their cell phone. People are creating poems, they're writing novels, they're doing all kinds of creative acts on their phones. That's where they work. And it should just be taking their stuff, right? You should be valuing it in a market. And they should get reimbursed. They should get valued for the work they're doing. All right, so this model doesn't even talk about that. We have to start talking about that. All right, so I actually take this seriously enough that I've been working in a context of a company where I am the chief scientific advisor, and that's the CEO there, my friend Steve Stout. He's a legendary music producer in the hip hop world. And about 5 years ago, he started this company called United Masters, where I participate. If you go online to that company, you'll see it's a very active, very interesting place. So it is a three-way marketplace, okay? So if the context for all this is that, music is being treated wrong. There's no market for it. It's kind of weird because more music is being listened to than ever before in history right now, by far. More people are making music than ever before in history. So it seems like a total success story of computer science, right? But now if you look at the data, 95% of the songs being listened to today were songs written in the last 6 months. And there are songs written by people you never heard of. Okay, how can that possibly be? Isn't everyone listening to the same artist? Well, no, not at all. Okay. Oh, that's interesting. So who are these artists? Well, they're like 16 to 20-year-olds typically. They're really good at making music. They make it, they put it up, and then it's on the web. It's a device on the web, and then Spotify grabs it, steals it, and now Spotify effectively owns it. They sell it. They make money. The artist doesn't make the money. Now that's kind of sounds unethical, but it's even worse than that. This 20-year-old will do that, and they're not going to have a job, and they don't. By age 25, they have to move on and do something else. Okay, so that's just wrong. All right, so the first thing you can do is say, okay, there must be an underlying market here. There's producers or consumers and all that. Let's think about what is that market? What's the data flow to support that? And what are the economic principles needed to support that emerging market? How can we make that market emerge? So the first thing you do is you make data flow. So if you're a musician now at United Masters, and there's now about 2.5 million musicians, this is really working, who are United Masters artists. They sign up, and every week they get a data analysis. They get to see a map. This is the United States, so they see a map of the United States. And they see every time one of their songs was listened to, they see a dot on the map. So they can see that, you know, in Toledo, Ohio, that 10,000 people listened to their songs the last week. They didn't know that. That's really interesting. So they tell the people in Toledo, Ohio, look, I'm popular in your city. They look at it and say, yeah. And so they have you come give a show there and you make a few $1,000s. Okay. And if you do that a few times during the year, it starts to become a salary. And these artists are able to do that. All right. But it's really a multi-way market. So you bring in brands. So Steve went to the National Basketball Association. The National Basketball Association, if you go and watch a clip, there's music behind it. Okay, where's that music come from? Well, Steve said, who are you getting the music from? And they said, well, from the record companies. You know, Beyonce, is anyone ever listening to that? So he says, no, people are not listening to that. And so anyway, long story short, he signed a contract with the NBA. And so the NBA music now is all coming from United Masters. And so every time you watch a clip, if you do, this is also true for FIFA, if you're interested in football, you watch a clip there and there's some music behind that. In that moment, the musician got paid. Okay, so that's also part of a salary. And then the musicians are connected to listeners who they can make offers like, I'll come play your daughter's wedding and so on and so forth. And this is now an emerging market. Now, where's the AI and machine learning behind all this? Okay. Well, part of my point is it's not that complicated. It's just data analysis and making a network and making it adaptive, but also doing the mechanism design principles so that it's a fair market. So it rewards people appropriately. There's good incentives. It has all the long tail handled. It does matching correctly. All of those principles needed to be part of building that system. Okay, and so they were. So this is one of the first systems I know of that's a real alive mechanism design with machine learning. Why the machine learning? Well, because it's being done at scale of millions. You can't have someone write down their preferences. I like that musician, and all that, like an economist would have you do. Okay, so I could go on about that, but I hope you get some sense. This is, something real. This is creating new jobs. And AI is often talked about as a place that you lose jobs, which is going to be true, but it doesn't have to, and this is a great example. So this could happen in any country around the world. You could create probably a few million new jobs just in music. Now think about doing this for journalism or other creative acts. Okay, so this is real. This is something often called the creator economy. And I think as mathematically inclined people, we should be contributing to that, and not just letting it sort of not be talked about. Okay, so that's that. All right, so recommender systems are part of the machinery behind a lot of these things. They are pattern recognition systems. And again, you've all sort of worked, you're used to these at this point. And now let's think about the economics of recommendation systems. Okay, so recommendation systems are thought of not with an economic model in mind, just like the federated learning. They simply make recommendations. Isn't that good? Well, if you think about how they're used in a bigger system, maybe not. Okay, so if you recommend things to people and many people start to use your system, you could recommend the same entity to many people. Okay, so a recommendation system for movies, like Netflix makes recommendations, and they might recommend the same movie to 100,000 people today. I'm sure they do all the time. And there's no scarcity in the computer science world. You just copy the bits and you send it to whoever needs it. Same thing with books. So you can copy the books really quickly. What if you start to recommend things in the real world, like restaurants, where there's scarcity? You can't copy the restaurant. All right, so what'll happen is that if you make the same restaurant recommendation to lots of people, you'll create congestion. All right, so it's kind of obvious. All right, so there's scarcity. All right, what if you recommend streets to driver? What's the fastest route to the airport? Well, that route's the fastest. I'm going to recommend that to everybody. Well, obviously I will create congestion. Okay, so now how do you fix that? Well, again, this is nothing mind-numbingly complicated about this. But if you ask one of the computer scientists who are building these systems in Silicon Valley, how do you fix you created a problem? They'll say, well, load balancing. I'm going to make sure I only send 10 people to every restaurant, no more. I'll cap it. Okay, so, how are you going to decide which 10 people to go to that restaurant? Well, and this is ridiculous, but I've heard this from a CEO of one of the big companies doing things like this. They say, well, we know a lot about each individual. We collect all this data on them. We do their browsing history. We know their demographics. So we can predict which restaurant they really want to go to. So we will sort of take certain 10 people there, other 10 people here, and so on. And I hope you can see how ridiculous this is. This is insane, right? Humans don't want to be told by somebody collecting data where they should go to the restaurant. They want to be feeling like they're part of a market. They've entered into some multiple possibilities. I might like to go there because I've never had Southern Indian cuisine. That sounds interesting today to me. I'll go there. Or maybe this, or maybe that, or maybe I have some friends that told me about this. I want to be part of a flexible market where my utilities, my preferences are taken into account, not just someone guessed something based on my past data. Okay? All right, so that's a very simple point, but it's missed by Silicon Valley, basically. And it creates new mathematical challenges because getting preferences into learning systems, that's economics blends with statistics, blends with computer science. That's actually quite a number of interesting mathematical challenges. Okay, so the rest of my talks in this 3 weeks, in these three lectures, are going to now do the mathematics. So we're done with the background. I'm going to be talking about some subsets of topics here. The ones I think I've kind of picked are the ones in blue here for my next few lectures. How much time do I have today, Praneeth, left? Or who's got my, I didn't even notice when we started.
I think you started at 10 to 5. So
10 to 5. Okay, all right, so I got it. Okay, so there's a lot I'm gonna give you, there's papers behind all of these things. And it's definitely not just me working this, there's a kind of communities behind these things. And I'm gonna kind of pick also and function as kind of how the conversation goes after my first 2 lectures. The first one is the one I want to emphasize the most, even though I'm not sure I'll talk about that much about it. All right, but this is where the real mathematics comes into play. So in machine learning, we're extremely good at finding optima now, okay? We can find optima in high dimensional spaces, meaning hundreds of thousands or millions. And we can find them even if there's saddle points littered around, we can escape the saddle points. I worked with Praneeth where we showed how to optimally escape saddle points in high dimensions. And we, could do that in, all kinds of machine learning settings with these architectures and so on and so forth. So it's a huge success. All right, but in these systems we're talking about, you can't find optima, okay? There are structural reasons you can't find optima. You know something I don't know. And unless you tell me, the optima doesn't exist, right? Moreover, we don't want to be told from the top down, maybe the supreme being could look down and find an optimum and tell us all to go there, but that's not going to work in real life. It has to be done by local decision making. So those are equilibria. All right, so now if you look in the mathematics, of equilibria, the economists talk about that all the time. And it's not gradient-based algorithms, because gradient-based algorithms provably fail, right? Instead, it's these other kind of algorithms, most of which have never been studied in high dimensions with saddle points and so on and so forth. So there's a whole raft of problems there, right? Moreover, we're never going to arrive at equilibrium and stop. We're talking about the real world. So there's going to be dynamical, change of the equilibria. We want algorithms that'll follow those things robustly, not get knocked off too far, and track them and relax quickly and so on and so forth. Right? Maybe just give you one little kind of hint of some of the issues there. So the underlying mathematics is just kind of like fixed point theory. So von Neumann would would nod his head to this. Of course, fixed point theory. You don't see many algorithms for fixed point theory in machine learning. It's all about gradient descent and variance, right? So, but fixed point theory is different, but it's still just vector fields. So think about gradient descent. I'm in a space of some kind, there's a vector field in my space, okay? I arrive at a point and I see a vector leaving that point and I follow that vector a little bit, okay? I follow the gradient. Or maybe there's something called momentum and I follow a little bit like the last 2 gradients and I move along quickly, hopefully, in high dimensions. Now, here's another vector field. Let's think about a vector field that has got curl to it. So let's think about a vector field where there's circles in 2 dimensions, say, circles, and at every point in the circle, the vector is tangent to the circle. It just goes around like this. So I've got curl. I have many circles like that. All right, so first of all, what should be the solution concept here? Okay, well, is there any special point in that space? Yeah, there's one in the middle, it's called the fixed point. It solves a variational inequality. And I'd like to find that point. Right? I don't know where that point is in some high dimensional space. I just have this flow. All right, so maybe I should try gradient descent. All right, so I arrive at a point and I'm going to follow the gradient a little bit. Now, if I follow it a little bit, I'm going to be outside the circle I just started on. If I follow it even a tiny bit, I'm going to still be outside the circle. And if I do that again on the next step, I'm going to be further outside the next circle. I'm going to spiral out. All right, and that's just a fact. Gradient descent fails badly in fixed point problems. All right, is there anything that does work here? Well, there are algorithms that do work. And so just to give you a hint of the kind of algorithms that do work here, if something's always spiraling out, that suggests there must be an algorithm that does the inverse of that actually works. What if I just ran time backwards? I would spiral in. All right, and that's called the proximal point algorithm, and it succeeds in this case. It's just more computationally intensive, and then there's approximations to that, like extra gradient. And now you want to do them in high dimensions, stochastically, and blah, 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 blah. All right, so even in bullet number 1, there's just a very number, there's a lot of papers that haven't been written yet. There's a lot of cool things to do. All right, but what I really want to get into are the issues that have more of an economics flavor, not just equilibria, so incentives. That's going to be the big word for the rest of this talk, and then my other 2 talks. If you don't do machine learning with incentives, then when you roll it out in real life, it's going to be a mess. And I'm going to give you some examples of that and how do you talk about fixing that using economics ideas. All right, so the rest of those things have to do with either 2 topics, incentives or uncertainty quantification. Uncertainty quantification is the elephant in the room with all of the latest deep learning stuff. They do not know how to say, I'm not sure. And there's various ad hoc heuristics. They just don't do a good job with that though. And they can't give you like confidence intervals. Okay, I'm not sure, but I know the truth is somewhere in the middle. Okay? They don't do that. So we're going to be talking about how to do that in the modern large-scale world. Okay, last point before I turn to some actual algorithms and theorems is that most of what I've been talking about has been motivated by spending time out of academia, like in industry. I spend a day a week in various industries over many years. But if I return now to academia and I think, okay, what are the implications for academia of this kind of way of thinking? Well, I think, okay, there are disciplines that emerged in the last century that are talking about information flows at scale and decision-making, all that. Well, what disciplines are there? And here's just kind of 3 of them that are, most notable in this sense. Computer science, the science of algorithms, statistics, the science of inference, and economics, the science of incentives, all right? Now, do they interact with each other, or are they just kind of islands into themselves? Well, they do. Computer science with statistics, that is exactly what machine learning is. Okay, it's just statistical principles, but done with computer science concepts, right? But machine learning has almost no economics in it. No talk about incentives, no talk about social welfare, and so on and so forth. So it's kind of, there's some, but just very tiny. What about statistics with economics? Well, yeah, that exists. That's called econometrics. All right, and econometrics is basically statistics on economic data with some causal inference issues. Right, it's mostly about measuring economies, and it's mostly for macroeconomists. It doesn't have much in the way of algorithms in it, or thinking about building systems that do economic kind of things. It's not what econometrics focuses on. What about economics with computer science? Well, that's a field too. That's called algorithmic game theory. And it's mostly about designing auctions and making them really, really scalable and robust in various kind of ways. And it's a whole field of its own too. All right. So that's really interesting that all 3 of these have interacted in very significant ways. All right. But each one of them misses the 3rd leg. Algorithmic game theory has basically no statistics in it. It doesn't take in data and adjust the algorithm, the auction or whatever, based on data. It just assumes things are known. All right. So this is an issue. And why do I care? Well, because when I do spend time in industry and you start to solve, say, I spend a day a week at Amazon. And so a problem might be the 3rd-party sellers, you want to sort of price various things like services that you're offering to them. And there's 100,000 of them and you got to do all 100,000 prices and there's all this data. How do you do all that to make it actually work? And around the table, you'll get 10 people and there will be one of, certainly of each of these disciplines. There will probably be someone in operations research to help blend it together and probably a chemical engineer. But in academia, you almost never get all those people together at the same table. Okay, so, all right. So now let's get into a little bit of actual concrete examples.
Can I ask you a question? Right?
Yeah, please. Yeah, please go. Yeah.
It's related to this. One could say that a big problem right now from recommendation systems that you mentioned.
Yeah.
Is that it's polarized the society.
That it's what?
It has polarized the society in
polarized.
Many ways,
yeah, exactly. Yeah.
And this doesn't seem to be any incentive with any organization, whether it's government or private organization, to address that issue.
That's right.
So I just want to get your thoughts.
They're absolutely right. It's a critical issue, and I think the young people in the room know this more than even the older people, how bad it is. And so you have to start talking the right language here. Part of it is incentives, right? And part of it is scale, and part of it is information flows and transparency and all sorts of other things. People are basically fundamentally good, but the system is incentivizing them to behave badly, right? And so one thing you do is complain about that, and that's what most people have done. Or you could be, in the CS companies and try to kind of adjust things a little bit. not really working. Or you can run to the government and say, regulate all this. And I'm not happy with any of those. All right, so the rest of my 3 talks are things I'm more happy with, which is let's think about what are some of the problems. I'm not going to focus on disinformation per se, but I'm definitely going to again and again and again return to what are the incentives and how do you bring them into the learning system? Because if you don't do that, you're not building it. You're not being a responsible engineer. Okay, so this first thing I'm going to talk about is very recent. We've just been finishing. I just worked on a paper this morning with Stephen, who's postdoc with me at Berkeley. Jake was a student with me at Berkeley, and Michael's a collaborator at Stanford. So what is statistical contract theory? So first of all, I have to tell you what contract theory is. All right, so it's one branch of the theory of incentives. All right, there is a theory of incentives. There have been Nobel Prizes given for it. It's not a, so the theory of incentives is kind of allied with mechanism design in economics. What is mechanism design? That's the inverse problem of game theory. You all know what game theory is. So game theory is I've got multiple players and they have actions and they do some action, maybe in sequence or maybe simultaneously, and out comes some outcome. And I want a good outcome, like a Nash equilibrium or some other nice thing, maybe. That's more like on the forward direction. That's like the science. If here's some game in nature, what is it? What behavior do I see? The mechanism design problem is the inverse problem, saying I'd like to see a certain behavior in nature. What game do I design to achieve that behavior? So it's a richer, more complicated problem. All right, so one branch of the theory of incentives is based mostly on Nash equilibria, and that's called auction theory. And you all know about auctions, so I won't elaborate. But auctions are situations where there's multiple players. They all come in. There's something to be bought, a picture, and they all are symmetric in some sense, and they have different valuations that are private information. And they're not going to just tell everybody their valuations. Again, if they did that, you could design an optimal algorithm that would do gradient descent and find out the best allocation. But you can't. People aren't going to do that. So instead, you design these mechanisms, which, when you put them in a game, lead to behavior that leads to the desired outcome, which is high social welfare or high revenue or both. And you all know perhaps about second price auctions that do this and so on. There's Nobel Prizes given for the theory there. So that's one branch. That's a very symmetric branch. That's where the equilibria are caring about our Nash equilibria, that everybody's as happy as they can possibly be individually, and they're all acting simultaneously. They write down their bid on a piece of paper. Lots of problems in real life are not symmetric equilibria. There's an asymmetry built in. And this is a part of economics that arose after symmetric, game theory and equilibrium theory. So this is called contract theory. In contract theory, there's an asymmetry fundamentally between one player and another player. So maybe I'm the boss of some company and I'm called the principal, and I would like to get something done, but I don't know how to do it myself, or I don't have the time or the wisdom, but I have some worker who's able to do it. But I got to pay the worker some amount, and I should pay them as a function of how well they're going to work, how much they already know, how much background knowledge they have, how efficient they are at doing so on and so forth. So I could ask them all that stuff, but they have a self-interest in trying to get paid a lot, so they're going to lie. Okay, if they're very efficient at making some product, if they hide that, then I'll give them a certain price, and now they'll make it much more efficiently than I knew, and they'll get a lot more money. So they will lie. All right. So that's called private information, and there's this asymmetry of information, and that reduces the overall social welfare. It's called information rent. Some amount of money is not available to the whole system because of this. You got to recognize that information rent. All right, so there have been industries which have recognized this, and contract theory emerged to help these industries do these kind of mechanisms. So these are now not Nash equilibria, they're called Stackelberg equilibria. They're in the context of sequential games. So there's a leader and a follower. The leader is often the principal and the follower is the agent, but it could be the reverse. Okay? Leader is the person who goes first, follower follows. And now that will lead to certain equilibria where no one wants to change anything. And you like to design good equilibria. So that becomes contract theory. And so now you all actually have experience with contract theory. In the airlines in the 1980s, all of the airlines were about ready to go out of business. A lot of the national airlines went out of business because there's these low price airlines that came in and cut out everything. Okay? And in that era, airlines had a single price for every seat on the airplane. You paid $100 for every seat, just like in a movie theater. You pay a certain price for every seat. And there was a smart CEO somewhere who got together with some contract theorists, and they said, what if we did it differently? So here, you know, and you all know what happened. That led to business class fares and economy and all that. So what is that? Well, the idea is that if I have a flight and I'm going from here to Mumbai, some people are willing to pay a lot of money to go because they really need to get there. And other people, they don't care so much, right? And so there's something economists call willingness to pay. And that's a hidden variable. You're not going to broadcast your willingness to pay. That would be dumb, right? So the airline says, okay, what we're going to do is we're going to create now not a single price. We're going to create a menu of options. So there's a price and a service, a price and a service. And we're going to give the same menu to everyone. Because otherwise that's called price discrimination and it's illegal and it wouldn't really work. If I decided that, you know, people who work at Google have to pay more because they obviously have a lot more willingness to pay, I would look at Praneeth and say, okay, Praneeth, you want to get on the airplane? It's going to cost you $1,000. And Praneeth would say, fine. And then I look at a student and I say, okay, for you, 100. And Praneeth would look at that deal and he'd start to dress more like a student. And maybe not a good example, sorry. Anyway, people will lie, quote unquote, because this is how humans behave. They look at the world, the game around them, and they play the game according to the rules. All right. So you know what the airlines did, right? They made these different fares. And so, you know, the students in the room will be very surprised about this, but there are people who are willing to pay $1,000 more for an airplane ticket because they can be first in line, they can have a bigger seat, they can have a little glass of red wine. It's amazing. And the students go in and they walk past that set of people who are very proud of themselves, and they're very proud of themselves because they paid only $100 to be on the same airplane, and they don't care about the red wine. All right, what is that? That's called social welfare. The overall happiness is high, and moreover, the revenue for the airplane is high. That's what you do in economics. You try to make everybody happy. And there's mathematics behind this, and there was a Nobel Prize. All right, now the problem here, from our point of view, is that this is not a learning system. Some person sat in a room and figured out how these curves should cross and what the menu of options should be, and they put it out there and hopefully it worked. And if they did, they got a nice salary, right? That's not going to be a lot of our problems, like the music problem and so on. Okay, so here is my, my example of how this really is, impacts the real world. So clinical trials are a huge social investment. These are numbers from phase 1, phase 2, phase 3 in the United States for various therapeutic areas. So, you know, hematology, you know, $15 million was spent last year for clinical trials. And you all know about this from like the vaccines. The vaccines were, you know, done very quickly. You ran 30,000 people through a trial. That cost a lot of money. Okay, so you'd like to kind of use this money wisely, but you'd also like to make good decisions. All right, so is this just a statistical problem? Because it sounds like it. You're just trying to cut the number of false positives down so you don't put bad drugs in the market, and also not have many false negatives where you don't kind of, you know, you catch all the good drugs. All right? Well, no, because it really is also a contract theory problem. There's a principle, which is the regulatory agency. In the US, it's called the FDA. And they are trying to be a good statistician. They look at each drug and they say, is it a good drug or not? I'm going to do a clinical trial with 30,000 people and I'll make a yes/no decision. There's some probability of a false positive or a false negative. That's statistics. Right? But they're not just getting hypotheses and data from the real world, or from out there, from somewhere. They're getting it from drug companies. Drug companies have private knowledge. They are going to give a candidate to the FDA, and they maybe know something about how good that drug is. You know, they know the biology behind it. They spend time on it. They even did a little internal testing. So they have some internal knowledge. But they're not going to just tell the FDA that knowledge for the same reasons we've been alluding to before, because the FDA will give them bad pricing. All right, so that is the real problem. And now let's think about the FDA as a statistician. So how should they do their testing? And here's kind of the setup. It's really a classical hypothesis testing setting. The drug could be either bad or good. Bad doesn't mean it hurts people, so they definitely do screening with animals and all that. They make sure it doesn't hurt anybody. But so bad means it just has no effect. All right? And there definitely are drugs like this on the market. They have no effect. The FDA sets up their testing with a clinical trial so that the probability of approving a bad drug is, you know, is controlled, like 0.05. It's actually 0.005. Okay, but roughly this. They also make it such that if it's a good drug, fate equals 1, that the probability of approval is something like 0.8. That's called the power. 1 minus that is the negative, false negative rate. All right, so is that a good test? Well, yeah, that's optimal. That's the Neyman-Pearson test. We have a theorem that says that that's optimal. Right? But is it actually a good test in the real world? And the answer is definitely not. All right, so here are two cases. In one case, there's a small profit to be made. It costs you $20 million to run the trial, And if you're approved, it costs you, you stand to earn and be $200 million a year. So this would be for some small niche drug of some kind. Now, in that world, the CEO can do this following calculation. They can say, if it is the case that my drug is not any good, which I don't know, but let's imagine that's the case, counterfactually, my expected profit will be minus 10 million. Because I'm paying this 20 million to play the game. All right, and so the CEO will look at that and say to the biologist inside the company, don't send a drug to the FDA unless you really are convinced it's good. You've done a lot of little internal testing, or you just really know, because it's going to cost us money otherwise. So in that case, most of what the FDA sees are good candidates, and then they do their test and everything is good, and most of the drugs will be good. That's mostly not what happens. What mostly happens is more like this, that it costs you $20 million to run the trial, but if you're approved, you might make 2 billion. So it's more like ibuprofen or something. And now you do the same calculation. If the drug is actually not effective, the expected profit is 80 million. Where's that coming from? Well, you only paid 20 million and you made 200 million if it's a false positive. Right? So you're super incentivized to send a lot of candidates up to the FDA, and people and drug companies do. All right, so a lot of approvals then are false positives, and they're now in the market. Does that hurt anybody? Well, it's not actually physically hurting them, but it's hurting our economy, right? And so what happens then is for a couple of years, it's just out there, and people start to realize maybe this isn't helping very much, and some other drug will come and displace it. All right, so can we fix this? And the answer is, yeah, this is a problem that as mathematicians we can fix. All right, so we're developing this area called statistical contract theory. I'm going to just tell you what it is. I'm going to state a theorem, and then I think I'm going to finish for today, and we'll continue on next time. This is actually a contract. Contract, remember, is like a menu of options and all, but it has a little more of a protocol around that. So an agent is presented with the following protocol. They can opt in or not. If they opt out, they just walk away and no harm's done. If they opt in, they have to pay a reservation price R, like 20 million. Then they choose a payout function from a menu. We design the menu, and that's again like this list of price, service, price, service, price, service. Okay? Services are things like license, how long you get to license a drug for, and so on. Now, the new part of this is line 3. This is not in classical contract theory. It only had line 1, 2, and 4. In this new theory, you now have a statistical trial which yields a random variable, a clinical trial, that's sampled from the true underlying theta. Because even though no one knows theta, nature knows theta. So when you do the clinical trial, you're reaching out to nature. All right, so nature supplies you a random variable, and then the agent gets a payoff, which is their choice of payoff based on that random variable. And then the principal has a utility, which is the amount they pay the agent. And then also, it depends on the truth, because after a few years, people will realize the FDA is doing its job or not, and they will have a reputation hit. Okay, so that is what we call a statistical contract now. And now the mathematical problem becomes, how do you design a contract? It's like the airline problem. How do you set up the fares and all that so that the overall system does a good job? What does that mean? Well, it means the overall system with all the incentives in play actually delivers good drugs to market, right? Okay, and so the last 2 slides, I'm not going to get into the details here, but just to say the following. Whenever you need to do something with economics, you have to talk about incentives, and you have to talk about there have incentive alignment. And so no big issue here, but really the incentive alignment story is that the expectation under the clinical trial, under the null hypothesis, if the drug is actually not effective, of the payment minus the reservation price has got to be negative. That's not true. The FDA just loses money, and they wouldn't play the game. Okay, so that's the assignment line. The classical p-value less than 0.05 is not incentive aligned. You can prove that easily. All right, so if that's the definition, can we state anything about how to design contracts? And so here's on one slide the theorem, which is pretty neat, which is we prove that a contract is incentive aligned if and only if, the only if part is the important part, all payoff functions are e-values. All right, what are e-values? Well, they're kind of like p-values that everyone knows about, but there's something a little different. An e-value is a random variable, x, such that the expectation under the null hypothesis of x is less than or equal to 1. So it's kind of the strength of evidence against the null hypothesis. In general, these are non-negative super martingales, okay? And because they have a martingale interpretation, they combine very easily. I can take multiple e-values and combine them in a nice way. I can stop them, and they have a lot of nice evidentiary properties that p-values don't have. Okay, so for a lot of us statisticians, these kind of are viewed as replacing p-values for inference. Anyway, with that as background, it's kind of amazing and cool that a contract is incentive aligned if and only if all payouts are e-values. So this is a statistical concept, and incentive aligned is an economics concept. And we're saying that those things are exactly the same. Okay, if you design with e-values, you know that things are incentive aligned. So this gives you a vocabulary on which to design statistical contracts. And so we've returned to our friend, the federated learning problem. And let me just say that we've written a paper doing this where you have the agents at the edge, the edge devices, signing statistical contracts, and their data is now being uploaded or not, depending on what they choose. And you can deal with things like free writing. If you have two people next to each other that have roughly the same data, one of them will look at the other, and if that person sends the data, I don't have to. That's called free writing. This avoids that. And it allows you to actually, value data, not just view data as something to be shipped and compressed. And this paper, we've had now 2 papers, and let me mention Harith Karimareddy, who's been the leader of this. He was a federated learning expert who's also now become a contract theory expert. Okay, and so tomorrow I will talk about strategic classification. I'll talk about uncertainty quantification and a whole bunch of other things that are probably a little more mathy. Today was meant to kind of open the door and show you that economics matters. Why do we want to do economics? Well, because in the real world you have to. And what are some of the concepts that start to come into play? So I'm happy to take questions.
Hello. Hey, thanks, Mike, for the talk. Learned a lot from it. So I'm a bit confused at the end because like the definition e-value does not depend on R.
Does not
depend on R, the
Yeah.
number, the cost, but then the definition on the left side depends on R, like the incentive line, right? So it seems weird that there's an if and only if.
Can you see that so the e-value here can be any statistic depending on the data, but it can depend on R.
Right, but then like if you have a e-value that doesn't depend on R on the right side, then how does it become?
It's just a scaling, right? So if I take that thing and I divide through on R on both sides, I can get a 1.
Okay.
Okay, so the family of e-values allows me to scale them, and that gives me different reservations.
Okay, so it's like there exists a scaling such that this is if and only if.
Yeah, it's in the family of e-values to have whatever scaling I want to impose on it.
Okay.
Yeah. Just say there's the paper that we're about ready to put on the web with Stephen and others goes a step further, and I may have slides for this by the end of the week if we get our paper finished, but it's a very interesting perspective on Bayesian statistics. Bayesian statistics is often not used for lots of real world engineering problems because you have to put a prior. Okay, we all know that as a problem. Well, in this principal agent setting, it's the principal that needs this prior. They don't know enough. The agents know, right? So we show that using this contract theory setting, that the principal can actually make Bayesian decisions without a prior, okay? Because they're getting choices being made by the agents which reflect their knowledge. Okay, so it's actually a possible new bridge that allows you to be Bayesian even in a frequentist world. And so I just, again, I think it's really, there's some depth here about these e-values, that they're a statistical evidence framework, but they are one that have incentive properties built in. And so you can now boost, you can use incentives. If you're incentivized to do something, I watch you do something, that gives me a little information. And if I do that again and again and again, as a good Bayesian, I can reap that information and actually do Bayesian inference, even though I never wrote down a prior. Yeah.
So this setting where you these contracts and this statistical notion of e-values. So what does it practically turn out to be in terms of the contract itself? What is the contract you would show a new agent that would come out?
So the contracts are measures of evidence. That's what an e-value is, basically. It's a measure of evidence. So if I, really have I'm pretty convinced that my drug is a very good candidate, okay, then I'm going to sign a contract where not a lot of evidence is needed, okay, because I'm already pretty confident. And that's going to, then the pricing is going to set up so that there's a low price associated with that. Okay, and again, before I set up the contract, I didn't know that about you. I gave that, you made that selection. That actually gives me information about what you know internally.
Thank you.
Yeah, so the E-values are sort of a mathematical, they're just maybe super martingales, right? And you could use the set of all possible E-values, that would be fine. It would just be computationally hard to work with. So you would want to choose subsets that have particular nice properties that, that you think approximate well the overall decision-making problem. Yes?
Does that lead to a notion of an optimal contract?
There is a notion of an optimal contract. Thank you. Yes, for asking. So the optimal contract is all E-values. So now it's optimal in what sense? Well, it's optimal in a statistical minimax sense. Okay, because I just told you, given a theta out there, what's the right thing to do for that theta? But I don't know theta. Can I do minimax over all possible? What's the worst choice of theta? And under the worst choice of theta, if I'm trying to protect myself in that situation, the optimal contract is all E-values.
I had a question.
Yes.
Sorry. In option pricing, I mean in math finance, in hedging of risks and all, we have a lot of optimization there. So since you mentioned about Stackelberg equation, so have you also looked into those kinds of problems where you work with max, min, and these optimizations?
I mean, the mathematics is definitely very akin to what we're doing here.
Okay.
But we're really trying to do these multi-agent game theory problems.
Okay.
And that's critical for us. So it's not really just trying to do hedging against the future, which is very interesting. I think I may talk about hedging and calibration in one of my talks. That's kind of a really interesting emerging topic. But that's really more about the probability prediction and making sure you don't lose money and the kind of the game theoretic interpretation. Sorry, not game theory, the game interpretation, playing a game. But we're trying to get really more into this multi-agents, trying to, interact with each other so there's an overall, good social welfare outcome. And how do you do that when there's data? Also, I didn't even mention this, but in the federated learning part, what's really interesting there is that the data itself is an economic good to be valued. And so that's really what the framework is trying to do. It's not just trying to say it's bits, but it has an economic value. And how do I assign value to that?
Hypothesis, what we do is that we fix the type 1 error and then we try to minimize the type 2 error. Here, can you illustrate how does this E-value will help?
Yeah, great question. So that's right. So as a statistician, this is always what you're doing. You're saying, okay, I'm going to be, this is what Naaman told us to do, is that, it's a constrained optimization problem. Make sure you have the type 1 error under control and then try to optimize the power, constrained optimization. In some sense, the same thing is happening here. We're just trying to say in a world with incentives and economic incentives, make sure the type 1 error is controlled. We did that, right? And if you choose all possible E-values, you maximize the power in a minimax sense, okay? If you don't care about that sort of approach, you might say, no, in my particular problem, I want to maximize the power against a certain set of alternatives. That would be a certain subset of E-values, right? So we're actually still back and very much in the statistical thinking. Naaman would not be unhappy with us. What all we've done is sort of to bring in contract theory into that part of it. So the overall contract is set up so that statistical inference is done correctly. And so in some sense here, the economics is subservient to the statistics. The goal of the FDA is not to make money. The goal of the FDA is to make sure good drugs go to market. But if you just treat that with pure statistical tools, that's not what happens. All right, so if you put some contract there inside the overall statistical thing, now good drugs go to market, provably. All right, so because people have been asking me, isn't it, oh, I see, you're putting some statistics inside of contract theory. No. And that's in some sense sort of obvious that, contract theory wrote all these equations. They said, oh, some econometrician, give me an estimate of that value right there. And then I put it in my contract. It's the opposite.
Question. So in physics, when we talk about high dimensional systems or landscapes and the motion from, let's say, one fixed point to another, etc.
Yeah.
We have the laws of nature actually guiding us doing that, Hamiltonians, etc.
Yeah.
In the stuff that you are dealing with, where do these laws come from? I mean, is it a sensible question?
Yeah, no, it's a sensible question. maybe in one of the talks I was going to get to, we'll talk about Hamiltonians and symplectic geometry and all these kinds. We'll be really borrowing statistical physics tools. And what it's that the value in that is to try to find ways to go as fast as possible. Okay, if I have a high dimensional space and a complicated landscape, for a physicist, it's just kind of, is there an end state and you get there? For us, it's how long does it take as a function of the dimension? Because the dimension's 100,000. If it was exponential in dimension, that would be hopeless. If it's even quadratic in dimension, that would be bad. All of our algorithms turn out to be logarithmic in dimension. And we have to prove that. The way we prove that is we go to tools from Hamiltonian, symplectic geometry. We get the geometry in. And the geometry then tells us the optimal way to go down or even diffuse. So the dynamics is coming in from a need to try to go as fast as possible because we're also being computer scientists, trying to get systems that go quickly in real life. We're designing them, so it's not really just analyzing, it's about design. So actually, here's kind of a mathy question that comes out of this line of work, which is that, Brownian motion, Einstein was kind of and finance people, it's kind of a characterization of a kind of dynamics you see out there in the world. And it's known to provably diffuse to a certain stationary distribution, okay? All right, but me as a designer, I say, here's a stationary distribution I want to diffuse to. And I started some other distribution. What's the optimal diffusion? It's not Brownian motion. It's probably, it's some levy or whatever. It's some process. Can I write down a variational characterization of the optimal diffusion that'll get me from one place to another as a function of the geometry? That's open. I mean, there's really some very cool problems there for the physicists who want to think. So physicists thought a lot about in calculus of variations about the optimal path. How I get there in fastest time, all that led to optimal control theory, right? With Hamiltonians and all that. But now if you turn it to stochastic differential equations, not differential equations, the optimal way to diffuse, I'm not sure that's been thought about. There is not a variational expression of that because really Einstein, they were just studying nature. They weren't trying to do like optimal control to try to get somewhere as quickly as possible. So yeah, a lot of interesting dynamics problems. That's one example.
Hi. You talked about United Artists and multi-sided incentives.
Yeah.
And if I'm right, contract theory is, I think, a two-person game here.
Sorry?
Is
Stackelberg?
Yeah, the contract that you mentioned is a two-person game. Can you generalize this to like a multi-sided game?
Oh yeah, no, definitely. We could generalize this to a multi-sided game. I mean, so there's all kinds, I mean, first of all, I should say we can, quote unquote, whenever I say we can, I mean, we think we know how to do, but it's really going to be a research project for the next 10 or 20 years. This is really, what I'm trying to talk about here is all brand new stuff in some sense. We're taking old ideas and putting them together in some new ways. But just like 20 years ago, I think when Parneet and I were starting out, everyone said, yeah, gradient descent, we know how to do that. And there's been 20 years of work to really nail it down. It's logarithmic in dimension, it can handle saddle points, blah, 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 blah. Same thing here. We don't know a lot of things, a lot of the details, a lot of the devil are in the details. Short answer is, yeah, we kind of have some sense of how to do that. But I want the young people in the room to be inspired that there's lots to do here.
So in your in one of the slides, you said you have if the drug is approved, there's a $2 billion profit and expectation.
The what?
If the drug is approved, there's a $2 billion profit in expectation.
That's right.
But you're assuming that you know the probability distribution of future realization of something that's going to happen. So this
no, you just take the data on that page, which is there was a certain false positive rate and there's a certain false negative rate. Because the FDA was being good statisticians. They did enough of this in the past, they know how to set up a test. Right? And given that, and given the amount of money is involved, done. I don't need any more.
No, but somewhere you're making some prediction about future, what the probability distribution of profits or,
not of profits,
revenues or all of that.
Well, I mean, so the FDA did all the statistics stuff, right? Fine. Okay. The actual numbers of like 20 billion or 200 billion, no, you have to estimate that. You have to have your economists sit down and sort of say, but that's called market study. You do a market.
So my question is that these estimations have all kinds of errors attached to them. Is that something that one is just comfortable?
Well, let me just sort of say, let's take off our mathematician hat for a moment. If you go in the real world, there's always things that aren't just coming out of the equation and out of the theory. And you've got to be a good engineer and sort of say, okay, I got to calibrate that. Where's that coming from? What if it's not right? How bad am I going to do? You got to be like a good CEO and think about all the consequences of using some math guy's, equation. If you use the Black-Scholes equation, And you get it wrong, you're going to lose a lot of money, blah, 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 blah. So these are guides. Let's be humble in what we're trying to do here. We're trying to provide guides. And a guide is often in the form, you're going to, in the next couple of talks, you'll see a bunch of equations that have got like 7 terms in them. K, N, log D over epsilon squared, blah, 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 blah. And one of those is an economics term. One of them is the learning term. One of them is a geometric term and all that. The whole point is how they come together. And so that you as a practitioner could use that as a guide. You're like, oh, if I got that term a little smaller, then things would be good. How can I get that term smaller? But what if it's not exactly right? Again, we're trying to build an engineering field, and good engineers are able to take the math, understand it, but also then work with those things and make reality out of it. Does that answer your? I don't know if it's answering.
So you're kind of saying that model uncertainty is not such an issue for mathematicians to address.
No,
Real world people just use these as guidelines, and they can.
I'm saying that the real world will have all these needs that we can't just write down an equation for. Model uncertainty is always critical. So just think about the data. So one of my articles that I referred up to there was talking about medical data. So, we went in and had a test done for a genetic test of some kind for a child that was about ready to be born. And they gave us a kind of a bad result. And so we went and looked at that. It turned out they had done the statistics fine, everything like that, but the data was 10 years out of date. And there had been a new kind of imaging machine developed in the meantime, which amplified noise in a certain way. So it was clear there was a provenance problem. And that's a model uncertainty problem. Ideally, when they collected that data, and now they realize the data is 10 years old, the model uncertainty would have grown to accommodate that. That's not going to happen, right? But then as a good user of that, you implicitly sort of say, well, let's look at all the sources of uncertainty and let's kind of put some kind of box around that model. And then let's do some thought experiments. And what if this happened? What if that? And I just, when people talk about like, jobs and where a lot of young people are doing, this is what they're going to be doing. They're going to be trained to do this kind of thing. Just like chemical engineers, hundreds of millions of people around the world became chemical engineers in the sense of actually making the chemical factory run, even though they weren't, just applying the equation. They were actually doing this. So this is hugely important to do all those kind of things. And the model uncertainty is not going to be solved. We have a bunch of approaches and they're guides. But then in the real world, you have to kind of put that together with local knowledge. Often, people know something about a particular local regime. People ask me sometimes, I'm going a little too far afield here, but who's going to dominate in AI? China or US? It's such a dumb question for many reasons. But one of them is just like chemical engineering, there wasn't a dominant country. Every country had a little different local conditions and they had different problems to solve. And so they trained their engineers to focus on those kind of problems using the overall tools. And they got really good at that. And each country developed its own version of the industry or aerospace or whatever. And then some of them got really good and they traded their knowledge with other countries. That emerged, a whole economy emerged. Same thing is going to happen here. Different countries will specialize. And it's really more about the algorithms are gradient descent, blah, blah, blah. The machines are the cloud, right? Everything is open and known. There's no secrets. This is not complicated. It's all about the engineers and the local knowledge.
It's a sort of a general philosophical question about your triangle. If you replaced economics by something a little more vague like sociology, do you envisage a similar sort of a coming together?
Yeah, no, it's a great discussion over a glass of wine or something if you want to, about what your academic landscape should look like and all that. And really, I hate to put that slide up almost because it's a cartoon. I don't really mean computer science. I mean computational thinking, which like numerical analysts. Sure. I don't mean just statistics. I mean anything with inferential information theory.
Right.
And economics, obviously, I mean social science, right? But and so, moreover, sociology and then law. Really, lawyers should be involved in sort of saying, well, wait a minute, those incentives might be correct, but there's also a liability issue and who pays for when it goes wrong and all that. What are the rules and should there be some regulation on that? So all around that thing is all of society, but it's just they're being configured in a new way.
But something that's not amenable to, not like social choice or something where there's some function you're optimizing or something like that.
So I don't like to be too rigid about these boundaries. I mean, a standard sociologist, if I read their paper, I usually don't understand it because it's very qualitative. There's no equations. I don't kind of get it, but sometimes the best papers, I get something. And as a guide to think, right? And I respect a lot of these disciplines for that. Also the lawyers, they have a way of adversarially trying to get to the truth. It's different from statistics who try to get to the truth with gathering data. And I respect that too. And I do think that what we're building is this cooperative endeavor of kind of all of the last 100 years of science coming together in a kind of a new way. And so I wouldn't exclude anything. I want anyone to welcome in. But in some sense, this is kind of a core. And if you really want to build these systems and manage them and be engineers, you got to learn our language. And our language includes equations, and it includes algorithms, and it includes incentives and all that. And part of the problem right now is we have CEOs and so on that go into various capitals and talking this. They don't know that stuff. And so that's part of the reason they're talking this nonsense.
Kind of related to this question, but it's a very pedestrian question. In a situation like healthcare, Medicare, there are a lot of debates. The question is that in deciding these policies in the government, do people like you, are you involved in making these decisions? Are these kinds of issues actually accounted for in deciding how much you pay up, what your...
That's a wonderful question. That really gets to what are we doing here, really, as a society, and what are our goals? And again, I like to look back to history a bit, so deciding how to regulate the chemical industry. It was clear there was some pollution at some time, and the government had to step in, and they brought in various kind of experts and so on. And medicine, regulation of medication and so on. Governments are not the best tool for that, but eventually they're critically needed. And they also set incentives. People realize the government's going to regulate a certain way, they do something different. But any individual one of us only hopes to have a little small involvement there. Okay, so I'm actually staying out of most of the big AI debates. I get invited to go to Washington and testify where I say no. I just don't think they are ready to hear the message yet. Instead, I go out and talk to young people and get them inspired to, when they make their own career, that they might say, hey, well, I don't want to necessarily write all those equations down, but I like the way they think, and then I'm going to go into government and I'm going to use that. Because right now there's just a dialogue of the deaf, right? So I think part of our role is also to get out there, write things in public fora. I did do occasionally a journalist I will go talk to. I didn't think I'd be doing any of this. I was just kind of a math person proving some theorems, but maybe I should learn more from the previous generations, but you don't want to waste all your time with lots of discussions that don't go anywhere.
On that, what I'm asking is this, that does the government, in making these decisions, there are committees which decides, Obamacare versus this care or that care.
Yeah.
Do they at all consult people such as you?
Well, I don't know exactly why you're asking. Every country's different. And so who cares about what the US is doing? Maybe you probably care more about what India is doing, because India consults its scientists. And I suspect in some fields, classical fields, physics or whatever, they did consult the scientists. I know in Europe they did. In this emerging field, not so much. But I take the longer view. I think we're in kind of a 5-year crazy window right now, where government's flying around, they all have to talk about it. They all have to have all these hearings and no information is being passed. After 5 years, information will start to flow, and I'm not sure exactly how it'll flow. But I respect the NIH and these other bodies. They put real scientists in there who really study things and they have real knowledge. And the vaccine response is an example. It was all ad hoc. It was all done in crazy ways, but it was put together by really smart people kind of deciding how to test a vaccine very, very quickly and get it out there. And so there's a lot of people I respect in those kind of jobs. Right now, though, I don't think the dialogue is very, very, very healthy mostly. And I guess I was kind of I love computer science. It's not my home discipline, I'm more statistics and math. I love it, but I was, in my talk somewhat critical, because I think the computer science training was just only about how do you put bits in the computer and how do you transmit them and how do you build systems that everyone will plug, like a cell phone, with no thought to the social consequences and no ability to think about them. And so the part of my goal here is to, again, put the young people in the room, say, hey, you can think about these. You don't just have to kind of keep building things and hoping that it works, and then screaming, no, it doesn't work, government, come help me out. No, there's going to be another path, which is a little bit more of a serious, what concepts are missing, how do I put them in, who do I talk to get them to be socially valuable. But things are moving so fast also that it's not clear how to do this. If I could change social networks, I would have, but it happened so fast.
Yes, if there are no further questions, let's thank Mike.
Thank you.